Welcome everyone. My name is Tim Skell, HVAC Application Engineering Manager. Today we'll be going over some HVAC 101. We're going to use the building I'm sitting in today as a case study and review its HVAC system. So what we'll take a look at are the major components of an HVAC system. Chillers, pumps, fans. We'll talk about how an HVAC system operates. We're going to talk about the role of VFDs in HVAC. And also, as we're going through this, keep in mind all of the available data and how valuable that can be, whether you're trying to learn about your building, energy savings, or just straight up troubleshooting. So the building I'm in, it's in New Berlin, Wisconsin. So yes, I'm a cheesehead. We're almost 150,000 square foot. What's unique about this building that we'll review today is it's a multi-purpose building. About a third of it is office space and about 2/3 of it is production assembly space. So each area has its own unique needs and challenges. So the air handlers that feed each area are designed specifically for that area's needs. What does this building look like? Well, let's start out by talking about this picture right here. So this picture itself, this is a screenshot from our operator workstation. This is essentially my computer that lets me access our building management system. I might switch between building management BMS and building automation system BAS back and forth in this presentation. To me, tomato, tomato as far as BMS or BAS. So as I look at this graphic right here, I can see a lot of pieces of information. So I'll start with the right side of the building right here where all these colors are. These are the different office areas. So I have a air handler here, which we'll actually talk about on the next slide, that feeds these zones here. Each one of these zones has its own temperature sensor, so I can see if it's happy and it's right near set point, or if it's getting further off, whether it's too warm, whether it's too cool. And then there's another air handler for this half of the office here. And there's office air handler over here, and air handler 7 feeds these areas here. So then I take a look at these dark areas. These are production floor, receiving areas. These environments are a little bit different than offices, where in the office, I have a lot of different zones that need to have different potential set points for temperature. I might have a conference room with lots of people in it next to an office space that has nobody in it. Where production, this is just one great big wide open space. After I talk about this air handler later today, we'll talk about this air handler here, and you can see how these different pieces of equipment have different functions and features based on the area need that they serve. So now let's take a look at an example air handler. This one happens to be air handler up on the roof to feed half the office space. So what I'm going to do is start out by just following the airflow through this air handler, and then I'm going to take a look at the individual components. So as we take a look at this drawing here, if you have not seen an air handler in person, the physical air handler, it does not look like this image where it looks like an eye with a big tail on the top. This is meant to be a graphical drawing of what's going on. This isn't what the actual physical piece of equipment looks like. So initially high level, you're going to have outside air come into the air handler. It gets mixed with some return air. We'll get into those details in a little bit. There's some filters in there. Make sure there's no leaves or anything coming from outside coming in. There's a fan that blows the air. And then there's going to be some coils that either heat up or cool down that air based on what's going on. There's some safeties we'll get into, might get humidified, and then the air just goes out into the space. Then it goes into the room that me and you might be in. It warms things up. It cools down the room. The air gets warmed up from our bodies being in there. It gets treated as what's called return air, comes back in here and either gets blown outside or gets circled back. So that is the very high level. So of an air handler. So what I'm going to do now is go through a little bit more detail here. So as I take a look at this detail, you've got air monitors coming in here, looking how much air is coming in, and these mixed air dampers right here. So why exactly do we have these? Why do we have some return air coming back this way? And in other cases, we were using outside air, and in this case, we got 42% from outside, 58% return. So why do you do that? Well, let's consider the situation where it's 95 degrees. Yeah, we don't get a whole lot of 95-degree days in Wisconsin, but we get some. So 95 degrees, and I'm trying to cool my building. Well, does it take more energy to take that 95-degree air and bring it down to, say, 55-degree air for cooling? Or would I rather take, say, 75, 80-degree air and cool that down to 55? Well, it's a heck of a lot easier to cool down 80-degree air than it is to cool down 95-degree air. So on those really hot days, you bring in less outside air and you use more return air. Now, I'll swap it around, and my more typical day in Wisconsin, it's a little bit cooler. So what I can actually do is use my outside air for cooling, and then I have very little return air coming in here. So if it's 40 degrees outside, well, believe it or not, my building a lot of times is still in a cooling mode, even when it's chilly outside. So I can take that 40, 50, 60 degree outside air and bring a lot of that into my building for cooling. So that's why you have these mixed air dampers right here. It makes you decide how much outside air do I want to use versus return air. I would say that with COVID and things like that, obviously that changed the approach, and there's a lot more view of bringing in outside air and a little bit less attention paid to the energy savings aspect when you can bring more fresh air in from outside and reuse less return air. As I mentioned earlier, there's also air filters in here. There's going to be temperature sensors in here to see actually what the temperature is of this mixed air, so that way it can adjust appropriately, sees exactly what's going on. And then there's a supply fan here. So this could be one large fan. This could be many small fans. So there's a VFD on this fan, and that controls how fast this fan is operating. And this air, that once it leaves this air handler, goes into a duct system. And I'll show you what's called a VAV, variable air volume box, on the next slide. And those VAV boxes will control how much air go into each room. So based on how many of those boxes are opening and asking for lots of air versus how many are closing and putting just a little air into those rooms, we're going to speed up that fan as needed to maintain a specific duct static pressure. So you can see there is some information that we can see on the graphics here. You can see it's on. It's being told to run at 31 hertz, and yep, that's what it's actually running at. The motor is drawing 2.2 kilowatts, and it is not faulted. So there's a little bit of data there. We can do better, which we'll talk about in a little bit. So now that the air's come through, on the graphics here, you've got a chilled water coil and a hot water coil. So if you're in cooling mode, obviously you've got some chilled water coming through here, and we'll talk about chilled water later today and where that comes from. So right now we're just going to assume that this cold water just magically appears at the air handler, and that's how we cool down the air. You got air coming through a coil, the coil's got cold water going through it, and it cools down. If it was winter time and I was trying to warm the air up, I'd have boilers make hot water, and I'd be warming the air up. Then you got some safeties here. So you got a freeze stat. So let's say something bad happened and my equipment wasn't running, and it's one of those minus 20-degree days in Wisconsin. Last thing I want is my coils to start freezing up because I'm blowing minus 20-degree air through the air handler, and coils freeze, ice expands, things break. Not good for anybody. So you have freeze stats here that are safeties that say, hey, something is wrong. It's way too cold in this air handler. Let's shut everything down. So that's what your freeze stats are. And then this last little part here is a symbol for humidity. If the space is too dry, we can add humidification, add humidity to the air to make it more comfortable. On production floor units, something where you're building electronics in Wisconsin winters where it has the potential to get dry, you can believe static electricity not good for when it comes to as electronic assembly. So we make sure that we keep the production side very humidified, high levels of humidity to make sure you don't get those static shocks. So that's another little part of the HVAC system is the humidity levels. On the graphics here, you can see there's various statuses here. So I can see my humidifier is off right now. Summertime, don't really need to add humidity. It's more of a winter thing. I've got my duct static pressure here. So there's some really cool things we're doing from energy savings aspects, where if I see a lot of my VAV boxes, which we'll talk about in a little bit, but basically if there's not a lot of demand in the system for cooling, I'll actually lower my duct static pressure set point. So those are some energy savings things. It's a little bit beyond the HVAC 101, more of a 102 conversation, but just be aware there's some pretty cool control strategies you can do to reduce energy consumption in your building when it comes to the HVAC system. And then I got some safeties here, some of my freeze stat, which you talked about here, the freeze alarm, smoke alarm. So let's say there's a fire and there's smoke coming back in the return air. Air handler senses that. What I don't want to do is take smoke from one part of the room over here, have it come into my air handler, and have it then come back around here and get blown into another part of the room. That's a very bad thing. So by default, everything shuts down if it senses smoke in the return air, unless somebody comes in later and puts it into fireman override mode, say the local fire marshal's on site and he has the ability to override things. So that's a whole nother level of control. But for the most basic air handler, when bad things happen, it shuts down. So you can see status here. These safeties all get wired back into the VFD that's running this air handler. And then this whole system is connected via what's called BACnet. And that communication protocol brings all this data back up to the computer so I can see exactly what's going on. So there's been times where we had a nuisance fault once on a high static safety cutout, and this particular air handler's up on the roof. For me to walk to one side of the building, get the roof access, walk all the way back to the other side of the building, it's darn near a 10-minute walk, and then you'd have to start troubleshooting. But the beauty is if you can see what caused it to trip off here, you can start troubleshooting before you even have to get on the roof. So that's what the nice thing about these building automation control systems is, just brings so much data to you and really helps you troubleshoot. One last thing I should probably mention is you see a little thing down here, CO2. So again, this was a little bit more pre-COVID, and some of the design changes have been altered since then. But what we would actually do is we'd look at how much CO2 was in the room. So carbon dioxide, me and you are sitting here today having a conversation, we're talking. When the CO2 levels would go up, we would bring in more outside air. When the CO2 levels would go down, we'd be willing to use more return air. So that was kind of a variable in how we controlled these mixed air dampers too. It wasn't just purely looking at the temperatures, we were also looking at the CO2 levels. Next, let's talk about variable air volume VAV boxes. So I mentioned this very briefly on the previous slide. So we know that air handler creates 55-degree air, and it's sending that out to the building. But what if I've got two situations? I've got a conference room, that conference room is full of people, and then right next to it, you've got an office, and that person likes it at 78 degrees. They like it warm in their office. But all I've got is that 55-degree air coming from the air handler. Well, how does my HVAC system handle this? So what you've got are these VAV boxes here, and you've got the 55-degree air coming in. And let's look at that conference room first. So what's going to happen is if it's warm in that conference room, this VAV box is going to open up and dump all kinds of 55-degree air into that room to help keep it cold. If it's getting too cold, it'll start to close off and bring less 55-degree air into there so it can hit that set point, whether that's 73 degrees or whatever you got that set point to be. Right now, in this image, you can see it's at 71.5 is what my actual temperature is at. And my set point is to be at 73. But now if I've got an office space right next to it, if I dump a bunch of 55-degree air into that room and that person wants it 78 degrees, they are not going to be happy. It's going to be ice cold in that room. So the first thing that happens is this VAV box is going to start to close off, and it's not going to dump nearly as much 55-degree air in there. It's always going to have some air come in, and these things can be adjusted as far as what are my min and max CFM that I would want going through that VAV box. But you always need some air because you don't want to get stagnant in there. You want fresh air in that room. Otherwise, somebody might start taking a nap when they're at work, and then nobody's happy. Well, the person taking a nap might be happy, but the management's not. So what's going to happen is this VAV box is going to pinch down as much as it can and bring as little fresh air as it's allowed to bring in. And if it's still too cold, then what's going to happen is this valve is going to open up, and this is a VAV with reheat, and we're going to reheat that air. So it came in at 55 degrees. If you open up this valve, that'll warm the air back up, and that'll bring warmer air into that room. Now you might be thinking, man, this is really inefficient HVAC system. So you spend electricity, use electricity to cool down this air, and then you use electricity to warm it back up. Yeah, that is true. So there are some creative things you can do with designs to really reduce that energy consumption so it's not really as wasteful as you might think. So when we talk a little bit later on the water side of things, I will show you something called a heat recovery chiller and how we use some warm water that gets produced almost for free to handle this portion of it. So it's not quite as inefficient as you might think. So if I come back to this air handler again, and I mentioned earlier that we have the VFD on here and there's some data that we're showing. Really, there could be more. I mean, the beautiful part about things like BACnet and building automation systems is it's just oodles and oodles of data that can be brought up. So let's take a look at these two items. That drive right there has these things being shown and it has those safeties I talked about are wired to the drive and brought back out. But other things that could be talked about are over here. Well, we've got handoff auto status. So the drives are typically in auto mode. That way they can follow the building automation system. But every once in a while they might get put in hand. Somebody needs to override something. Maybe something's broken. Maybe they're doing maintenance on something. They put something in hand. And that's fine. That's the whole reason the button's there, right? Is to put something in hand, put it in manual mode. But far too often they get left in hand mode. So somebody needed to make a change, so they put it in hand, they manually did it, and then they walked away and they forgot about it. 1 hour, not a big deal. One day, not the best. A week, a month, sometimes years, the amount of energy being wasted is unreal. The whole purpose of adding a VFD, there's really two reasons. One is to be able to control that flow, but a very big advantage to controlling it using a VFD and variable speed is energy savings. You get big energy savings by slowing things down with a VFD. And if somebody puts it in manual mode and they just sit there and run it at full speed or some very fast speed, they're losing out on all those energy savings. So what a good automation system can do is they can bring that data back to their operator workstation or throw an alarm when something is in hand mode so that way it isn't forgotten that it's in hand mode. Same thing in bypass. Let's say a drive fails and they throw it into bypass mode, so it's just running full speed. That's very good short-term solution if the system can handle full speed, but you don't want to leave it at full speed because again, you're wasting energy. The VFD is there for saving energy. How about resetting of faults? So I mentioned earlier that some equipment it's going to be up on a roof and it could take a bit to get to. So certain faults they're kind of less critical. If it's a VFD fault, I could actually set up the system to reset a fault on the VFD via my operator workstation. I can display what the fault name is also, so it's very clear, so I know which ones are critical that I better go up and put my own eyes on versus which ones I can just hit the reset button from remotely. So having that fault name come out would be really big. And then another one I always like to have on operator workstations is kind of talking about torque, specifically broken belt indication. So that way, if I had, there's always some type of connection between that motor to the fan. One common type of connection is a belt. So if that belt was the brake, yeah, my motor's still spinning, but my fan's not moving air anymore. So if I have broken belt indication on my VFD, I can be alerted of a problem before I have to wait for rooms to get too hot or too cold and people to complain about it. So I can proactively find out something in my fan is not working. So even though this is ABB's own HVAC system using ABB's drives, when our building was first designed and commissioned, some of these low-hanging fruits weren't even installed by the controls contractor. So these are things for what people will call continuous improvement, continuous commissioning, things that you can add to your system as you get to learn your building and realize, you know what, I'd like to have this piece of data shown on my graphics or that piece of data. So that's the beauty of HVAC and control system is that there's always opportunities to improve them. If we're talking about data, we definitely need to talk about trends. Another really neat thing about building automation systems, especially those talking BACnet, is with all that data available, you can graph it. You don't have to be watching it instantly. The building automation system can graph anything you ask it to graph. And then when you need that information, you can go in and say, you know what, from Monday at 2 p.m. to Monday at 5 p.m., somebody complained about something. I want to go see what was going on there. So I can pull up exactly when I want to graph it. So here's just a couple examples. Here I'm looking at power consumption on my supply fan. I can clearly see from 8 o'clock to 4 a.m. that this particular unit is turned off. Then I can take a look at its power consumption through the day. I can change how often I pull this information. I can ask for this information once a minute. I can ask for it once every 15 minutes, once an hour. Depends on how important that data is for you. I can look at discharge air temperature coming out of that air handler. It's kind of neat when you start looking at things like this, like, yeah, it's stagnant air, so that one really doesn't matter. But I can then see that, you know what, up until 8 o'clock in the morning, I was okay sending out 60 to 62-degree air in order to cool my building. More people started coming in, so I had to adjust my set point down to 55 degrees and have 55-degree air come in. I was probably also using outside air for my cooling here, and then I had to use a little bit more of my chiller, have my chiller turn on and get 55-degree air because my outside air just wasn't enough to cool the building. So a lot of really neat things you can see what was going on based on these graphs. I can look at building pressure. This was an important one for our building in particular because we had issues where the building pressure had gotten too high, and then it created a security issue because your doors weren't shutting and latching because there was too much pressure. But at the same time, we wanted a higher pressure because as you got semi trucks that are backing up and either loading or offloading our products, either bringing parts in or shipping drives out, we don't want all those fumes from the exhaust from the diesel trucks coming into the production area. So we want high building pressure to keep the air going out instead of coming in. So we had some fun balancing acts in order to maintain security so our office doors would shut, yet we weren't sucking in outside exhaust air from the diesel truck. So we were doing a lot of graphs on building static pressure. You can kind of see here there's a spike when the building was unoccupied, then at 4 a.m. everything turned on. Well, it took a little bit of time for everything to catch up and stabilize. And it's not just looking at a single graph. I can take all kinds of information and put it on a single screen, and I'm good to go here. So a lot of information can be found on trends. And when it comes to trends, why stop at just HVAC information? You can actually go above and beyond that. So what we did with our building is we took our building's power meter and we integrated that into our building management system so we could see it on our operator workstation. So I could have trends just like my HVAC trends, but I could trend my building's power usage over the course of the day. I could also take a look at my building's power factor over the course of the day, which for us was really important because we were getting billed a power factor penalty from our utility. So we were able to look at this, figure out what exactly was going on that was making our power factor dip at these times of the day, correct that, and save ourselves thousands and thousands of dollars in power factor penalties. So as you're looking at setting up your operator workstation, don't just think about your HVAC system. What else can you integrate to make that information readily available for yourself? Another air handler I want to take a look at now is on our shipping and receiving. So I won't go through as much detail on this one as I did the first time, but I just wanted to kind of show a couple differences here with this particular air handler. So keep in mind, we're no longer feeding offices, so I don't have a bunch of VAVs uh, that are controlling how much air gets dumped into each office and hallways and cafeteria and things like that. This is just one big room you can think of it, one big area where we have products coming in and out based on semi trucks backing up. So what's really different here? Well, I mentioned there's no VFDs, so it's just a single zone that we're varying how much cool air we're putting into it and what that air temperature is. We're not worried about humidity in this particular area because there's no manufacturing or touching of circuits. And quite frankly, with big giant doors being opened and closed all day long, with trucks backing up and coming in and out, there's really nothing we can do on the humidity level for this particular area from an HVAC system. There's just too much potential for outside air contaminating the inside air. There's no demand controlled ventilation here, so I don't really care about the CO2 level coming back in because I'm just going to be bringing in a lot of air into here, keep positive pressure. And because, yeah, I mentioned earlier, it gets a little cold in Wisconsin sometimes, we added infrared heating over here. One thing I didn't really touch on the previous air handler was the relief fan. Somebody might call this exhaust. What this does is this helps take any air that's coming back and sending it outside. This also helps us maintain our building static pressure. So I talked about Want to keep things positive so we don't bring in too much outside air leaking in. We don't have doors getting propped open because we're exhausting so much air through our front door that the door won't latch shut. So what we can do is first you can open up these dampers here and let air naturally leak out. And then if the pressure is still too high, you can turn these relief fans on and help blow air out of the building. So when you're bringing a lot of air, fresh air into the building, that air has to get out of the building somehow. So right now I can probably tell that with this being closed, we probably have some big doors open, semi-truck backed up, so there's other ways for the air to get out of the building. Had this been open and this fan been running, that would have told me all our garage doors were shut, so we needed a different way for the air to exhaust from the building. Now, everything I've talked about up to this point has been more on the air side. I did reference that some chilled water magically appears at the air handler so we can cool down that air. So now I'm going to talk about where does that chilled water magically appear from. I know there's a lot on this page here, and we'll walk through and I'll simplify this into some smaller loops here. One thing I should mention is with this presentation, the building I'm in, it uses a chilled water system. Somebody might call it a chilled water plant to make that chilled water, which then ultimately gets used to cool down the air. There are more simplistic systems where it's just a single air handler. Somebody might call it a DX unit. There's refrigerant, a compressor, a coil, all in the air handler. It's kind of an all-in-one turnkey solution, kind of a little bit closer to your home air conditioner type system. If you go to your big box stores or your grocery stores, that might be what they have up on the roof. What we're teaching today is based on a chilled water system, which is a little bit more energy efficient, a smarter system. Everything is tied together. So let's look at some of these pieces of equipment. This right here is called a chiller. So its job is to make chilled water. So it makes chilled water, and I'm going to ignore this for just a moment and pretend this doesn't exist, this guy up here, the ice storage tank. So the chilled water comes out of the chiller, comes down here, and it goes out in my system. So what do I mean by going out in my system? Well, it's going out to all my air handlers. So I got these 7 different air handlers throughout my building that all need chilled water in order to cool the air down that's coming in from outside, or the return air needs to get cooled down. So that chilled water goes out to the air handlers that we talked about, and then picks up some heat and comes back. And you can see a pretty big delta T here from 38 degrees to 62 degrees. And that chilled water comes here. Now there's pumps because something's got to move that chilled water around. So we got a pair of pumps here that we'll talk about in a moment. That pump energy gets used to bring the water back up to the chiller, and the chiller then cools it back down from 48 degrees here to about 41 degrees right there. So the chiller cools it down and it just continues that loop. So let's talk about pumps here. So we got a pair of pumps. Only one of these is ever running. So this is called a redundant system or N+1 system. We got chilled water pump 1, chilled water pump 2. After X number of hours of this one running, this one will shut down and this one will run. The nice thing is then if one ever fails, whether it's the pump itself, the motor, the VFD, you've got the full backup over here. So that gives you a lot of redundancy, keep your system up and running. So the pumps are maintaining pressure in the system to make sure we got enough flow going on. So they do that based on looking at pressure. And then I said I was going to ignore this. Well, let's come back to that now. So one of the neat things we do here, and this is not a HVAC 101, this is a HVAC 201 topic, but just to give you a little teaser is this is a thermal storage tank, an ice storage tank. So what we end up doing is at night when our building's not occupied, we run the chiller when energy is low cost, it's cheap at 2 o'clock in the morning, and we make a big old tank of ice up here. And then during the day when energy is more expensive at 2 p.m., instead of having to run my chiller as hard as I normally would, I can bring my water through this vat of ice here. It's a bunch of pipes that have ice that build around them, and that actually cools down the water that way. And then I don't have to run my chiller as hard when the energy is more expensive during the day. So that's what this loop is right here, and there's some valves that control that. So this is kind of a general strategy for chillers. There are different control schemes. This is a variable flow single zones loop here. There are some designs that are 2 loops where you get a loop here and a loop here. That's not what this is. This is here specifically for the ice storage tank. So there's whole complicated presentations you can do on different chiller strategies. That's not my goal here to go through all those different strategies. But just like on the air handlers, though, there's a lot of data available here. So I can see that, hey, this VFD is running this motor at 47 hertz. It's not faulted, it's started. But again, there's a lot more data that I could bring back to my graphics if I wanted to. So let's take a look here. There are some things broken here. And I will pause for a moment. And if you happen to be watching a recording of this, you can pause your recording a little bit longer. I want to give you an opportunity to take a look for something that might be broken. I'll give you a hint. There's two things broken. And a third hint, which is not a HVAC 101, but there's some things that could have been further optimized that I'm not going to cover here, but I'm going to go over some of the things that are obviously broken just to kind of show you how helpful it is to have these graphics with the data. So there's my pause. If you haven't found what's broken yet, don't worry, you're about to see some red circles. See this gallon per minute meter right here? It says 0 gallons per minute it's coming through here. But if I look at this, it says, hey, this valve is at 18% to storage, so I'm using my ice tank for cooling. So I got my water coming in here. I got some coming this way, but I also have some of it is going here because I have 18% open. Coming here, water comes through here, and I know water's flowing because it came in at 44 degrees and it comes out at 32 degrees, yet I got 0 flow here. So this tells me my meter right here is broken. So this is something that actually when I took these screenshots to create a presentation, I let our facilities folks know that we had a problem and they were able to get that fixed. Also, when you look at some of these temperatures and things like that, there are some, you have some tolerances with sensors, so don't worry if you see something that's off just a little bit. But when you see something that's off a lot, that's when you know there's other problems. So what's that other problem? Let's take a look at this mixing valve. So this is used specifically at night when we're making ice. Basically, we shut down the rest of the HVAC system. We're not sending any chilled water out to their air handlers. We just have a real small, simple loop here with the thermal storage to make the ice at night. Well, it's at 0%, which is what it's supposed to be at. So that way all the water goes this way during the day. But if I look at my temperatures here, I'm at 38 degrees, 0.3, 38.6. Hey, there's tolerances. I'm not worried about that. Comes back, he got warmed up quite a bit at 62.5. Okay, that I expected it to get warmed up, but my water keeps coming this way. And all of a sudden it magically gets down to 48 degrees. Well, how the heck did I go from 62 to 48? The pumps definitely aren't cooling my water down. Well, what was happening is we had chilled water was leaking through this guy right here because the actuator was getting hung up and not closing this valve all the way. So it turned out that we were basically not bringing all the chilled water we should have been to the rest of our building, and it was a little bit less efficient. So again, I took a screenshot of this to create this presentation. I let our facilities folks know, yeah, we got a problem. They looked at it and they were able to get it corrected. So that just shows the importance of checking on your graphics every once in a while, just seeing what's going on. But you have to understand how the system is supposed to operate in the first place in order to know when there's a problem. So now we got physics. Physics says if I'm going to make something cold, something else is going to get warm, right? So my chiller was making chilled water. So that's what these blue pipes are right here on the drawings. Well, if I make something cold, there's refrigerant in there, and as you expand and compress refrigerant, you can make things cold and you can make things hot. That's just the refrigeration cycle. So when it makes things hot, well, now I have to figure out what do I do with that heat. So my chiller is inside my building, and I don't want it to be 130 degrees in that room. So what we have is a water-cooled chiller. Some people would put these outside and it'd be an air-cooled. Well, we have ours inside, so it's a water-cooled chiller. So I use water to get rid of that heat. So this water comes through the chiller. It picks up heat from the refrigeration cycle. So you'll typically see one of two things. The most common one is it's going to go straight to a cooling tower, and we'll get to the cooling tower in a little bit. But what we do is we use what's called a heat recovery system with our chiller. And remember when I said that you've had those VAV boxes and you have to warm the air up back up sometimes if you have somebody who's in an office and they like it warm in there? It seems really wasteful to spend electricity, use energy to cool the water, cool the air, to then have to then spend more energy to then warm it back up just for a specific office. So what we do is we take our condenser water, which is getting hot basically for free because we're spending all our money and energy to get the chilled water created, and this is more of just a side effect of it that's more of a nuisance for us. Well, let's take that nuisance hot water that just happens because of physics, and let's take advantage of that hot water. They also call it condenser water. So when the condenser water goes to what we call the hot water loop, which is specific for our heating system, and we leverage that condenser water to heat up our VAV reboxes during VAV reheats during the summer. But because of that, we have some extra hardware here. So I've got pumps right here with VFDs on to keep the water flowing. And then we have this right here, a plate frame heat exchanger. And what that does is it isolates our indoor water loops versus our outdoor water loops. Because what I'm going to do now we'll cover the other portion of the condenser water loop, the outside loop I'll call it. So we had, this side was our condenser water loop that we just looked at. Now we'll look at this outside loop here that goes out to a cooling tower. So what is a cooling tower? You can consider a cooling tower to be like a waterfall, but with a fan on it. So we've got this condenser water loop. It runs a little bit hotter than normal because that whole heat recovery system we had for using the VAV reheats with our condenser water going into our hot water system. So it's a little hotter than you might typically see. But you got this 100-degree water that comes here, falls down that waterfall, and starts to cool. A lot of times just having to go down the waterfall is not enough to cool it to what your set points are, where you're targeting. So that's where this fan kit comes into play. There's a VFD on that fan, and it'll ramp that fan up to faster and faster speeds based on trying to hit that set point of water temperature. So with that fan going full speed, you'll get a lot of extra evaporation, which causes a more of a temperature drop. If that fan is running slower, there'd be less evaporation. So it's all about trying to hit these set points. The VFD also has a bypass on it, the one that we chose, because that's a real easy way to get a backup, some redundancy from the VFD's point of view. So if the VFD was to fail, you can put it in bypass mode. Bypass means the motor runs at full speed, and when it does that, you're going to have lots of fan cooling across that cooling tower there. Now, a little bit confusing, good old HVAC terminology. This right here is also known as a bypass valve, which is independent, completely different than an electrical bypass for a drive, but the terms are both use the term bypass. What ends up happening is if you're running at full speed in bypass mode because the drive failed and you're actually getting too low of a temperature, what will end up happening is the bypass valve will then have some water skip the cooling tower and not go down that path. So that's what the bypass valve is, which is different than a drive bypass. Again, we've got redundant pumps similar to what you saw elsewhere. So we have a primary and a backup. Every 100 hours we'll swap there so we have equal wear and tear on it. And again, some data is here, all coming over BACnet, but there is more data that would have been available to pull out here. What about hot water side? So I talked about the condenser water from the chiller. And during the summertime, I do have that condenser water available, so I kind of can loop that into my hot water system here. But what about the winter time? So I need to warm up my air in the winter. So that's where we're going to leverage boilers. So one thing to be clear about these boilers here and what I'm talking about the hot water system, this is not your bathroom hot water. This is not your domestic hot water. This is hot water specifically for HVAC. So if I'm looking at a loop here, I've got boilers that'll bring in some water off here. Boiler pumps is what these BPs are off the main loop and warm that water up. The hot water pumps will then go ahead and pump that water through the system, comes back, and the boilers will warm it back up. So kind of neat energy savings things we're doing here. These two boilers are talking to each other. It's what's called cascade mode. So they know what's more efficient to run one at a really hot firing rate, or if I need to run two of them at a medium level. So they know where all those energy saving points are and when they should run one versus two. Also gives me some redundancy. If you haven't learned already, we really like having redundancy in our HVAC system. That's why, again, I have redundant hot water pumps here, each with VFDs on. Each runs for about 100 hours or so, and then they alternate to the other one to do the equal wear and tear on the mechanical systems. Equal wear and tear on VFDs, not really important, but equal wear and tear on your mechanical devices like your pumps, much, much more important. So I've been looking at a lot of graphical images from our operator workstation, but what does the room actually look like? So when you look at these pictures here, I will tell you right now, if you're new to HVAC and that's why you're watching this presentation, you're not going to see a lot of rooms that look like this. This is almost a showcase. You don't see chillers, which is what this is right here, behind glass doors like this. You can take a white glove and go in here and kind of wipe on things, and your glove's going to stay mostly clean, not fully clean, but mostly clean. A lot of times these chillers are shoved in a basement somewhere in some dark, dirty corner. Same thing in the background here, VFDs. I'll have another picture of that in a little bit. I look over here, here's an air handler. Sometimes these will be up on the roof. We have one inside, the rest are on our roof, so this is the air handler. So remember early on I said that a typical air handler doesn't look like a big giant letter I with a tail on it. It's a big rectangle box. That's what this is. And then you either got air being ducted out either up or down, this one being on the main floor, so it gets ducted up and out, and then the return air is coming in back here. I look at some other pictures here. I've got my VFDs. So these are my VFDs running my hot water, my chilled water, my condenser water pumps. I can see a couple of my chilled water pumps right here. You can see the blue piping. That's how I know they're chilled water. I got my primary and my backup that alternate every 100 hours on there. I got that orange piping up there. That tells me it's my condenser water. There's also some red piping up there. That's going to be my hot water. I can just barely see it right there where the condenser water goes into my hot water system. I talked about chillers. That's outside. That takes my condenser water and brings that temperature back down. That's what this box is right here with the big fan on top. And here's my waterfall media. So my water is kind of coming down along here. It evaporates and cools down. I talked about thermal storage, ice storage. That's what this big box is right here. Make ice in that at night during the summer when energy is cheap at nighttime. So that way we can use that to cool down our water during the day. Chilled water specifically. Again, nothing I've talked about today is for your domestic hot water, cold water coming out of a faucet. This is all loop specific for your HVAC system. So that's it. That's my building's HVAC system. So kind of summarizing what we talked about, we went over the kind of the major HVAC components, both at the air side and the wet side, the water side. So you got your air handlers that use that chilled water or hot water to condition the air, and then they use fans to distribute the air throughout the rest of the building through ducts. You got VFDs on those fans to speed them up and slow them down based on how much airflow is really needed. To get that chilled water in the first place, you got chillers that make the chilled water. As a side effect of making something cold, something else gets warm. That's called your condenser water. To get some of the heat out of the condenser water to continue that refrigeration loop, you have cooling towers involved. Our system happened to be unique where we use some of that condenser water and piped into our hot water system during the summer, so we can get basically free hot water for our HVAC system. If you don't have that, or come wintertime and your chillers aren't running, you got your boilers that make hot water. And again, it's all getting moved throughout the building with your pumps. And your pumps are going to have VFDs on to speed them up and slow them down based on system demand. And throughout all these graphics, there was a little bit pieces of data there, whether we're looking at the trends, whether we're looking at how fast the VFD was running, just oodles and oodles of data is available in HVAC systems. So if you don't have that data, if you go after this presentation, you go look at your operator workstation, you don't have that data, go ask your controls contractor, how do I get that data pulled onto here because I want to see it. And with that, just want to thank you for sitting in on our HVAC 101 presentation. Have a great day.